actually going through the number of those examples, but there are still important concepts that we need you to understand. So the first thing that I need you to understand before we can go into looking at scheduling algorithms are some of the fundamental aspects. The first thing is to try and understand that processes have what we call a CPU/IO cycles that they go through. That should kind of make sense to you. If you look at any code, there are portions of your code that really just uses the CPU time, and then it goes into a point in your code where it starts communicating with the output. And while you're waiting for the output, you're either stuck there or you go to sleep or whatever. Once you get some response back, then you continue again, you continue, and then you wait again for the output, and then you continue, and then you wait for the output, and then you continue, and so on and so on. So that is the type of cycles. You get cycles that really just iterate through these two environments. One of the things that the textbook talks to you about is the principle of what actually happens inside the CPU itself when it reads an instruction from memory. Remember, reading instruction from memory typically is also a little bit of an I/O, although in most cases it doesn't take up so much time. And that typically, when you have an instruction, it will go fetch the instruction first from memory, load that instruction into the instruction register. It will then decode that instruction register and then execute the instruction register itself. But sometimes it also has to fetch data, it has to then write data back. The best is to think about this rather from a CPU and I/O cycle principle. And the time it takes in between these two cycles are what we call burst cycles. So let's say, for instance, it takes 10 milliseconds for the CPU to do stuff, then that is what we call a 10 millisecond burst. Then we're going to do some I/O stuff, and that may put the CPU 100 milliseconds, and then it will do some CPU stuff again for a specific burst. So the principal idea of a burst is how long it takes in that specific portion of the cycle. We want to make sure that we distribute the CPU and I/O cycles successfully across our in the system itself. What is interesting is when they evaluated a bunch of programs and processes rather, they found that most processes has a large number of short CPU bursts and a small number of long CPU bursts. Meaning, in most processes, they spend a little bit of time on the CPU, and then some time on the I/O, and then a little bit of time CPU again, and then I/O, and then a little bit of time CPU. So very, if you think about the process itself, most of its time is actually waiting for I/O. That's actually what this thing says. There's a little, most of it is really just short bursts every time CPU, and then you're waiting for I/O again. So take this into consideration as we go through it. Very little CPU time very little time by a process actually spent in the CPU. Most of its other time just waits. It's kind of like, I don't know, public transport kind of thing. You're very little time where you actually drive and then you have to wait. And then you drive and then you have to wait. Okay, the next important aspect that you have to understand is the role of the scheduler. So the scheduler is a module that's part of your kernel of your operating system. It is in fact, well, you get schedulers that exist in user modes as well. We will talk about it a bit later on. But in general, when we just talk about process scheduling, the scheduler is in the kernel. It's a job of the operating system. And hopefully you can remember this is, when we started this course, I used this example. We said there's a very important component in your computer called the electronic clock. This clock keeps on cycling through and it creates pulses inside the computer. And one of the things that you can do is long-term schedulers you don't even need. You basically get them in mainframe environments, you discussed this in chapter 1 already. I think chapter 2 of one of them. And long-term scheduler basically selects from different jobs and decides which one to run next. But that's not a case typically where we focus on the PC. We did say in certain cases we may have a medium-term scheduler. Medium-term scheduler basically looks at the memory of your computer, and when the memory gets saturated, meaning there's no more space for me to put a process in, it will take the process that's already in memory and it will take that out of the memory, put it somewhere safe, so that we can free up some memory, so we can put some new process in, let it run, and later on we'll put these other processes back into memory. That's the job of the medium scheduler. So basically, they don't make it available for multitasking or multi-processing. Anyway, let's talk a little bit about, we've seen the short-term scheduler. It selects from the process that's on the ready queue. The queue is not ordered. The order of the queue is not important in most cases, but in other cases it can be. So we'll see why that is a reason why it's important. There are 4 times when the CPU scheduler gets involved. We've already explained now one of them, when the time quanta expires. That's what you call it when it counts down to 0. That's what we call the quanta has expired. The reason why we use the word quanta is because that's configurable. Some operating systems say 5 milliseconds, some say it's 10, some say it's 20. We actually can modify that as the operating system develops. The times when the scheduling decisions basically take place are common. Firstly, when it switches from a running to a waiting state. Now think about that again. When does this process switch from running to waiting? Either. So basically the process runs. Okay, I need to now save. Let's say this is an example. I need to save this file to hard disk. So save, open file, take, write. That's so write file. That's effectively what happens. Then it's stuck at that point. The process itself says, I'm now and I voluntarily let go of the CPU. So when that happens, it goes into the waiting queue. Goes into a waiting state. And as soon as that means I'm not running on the CPU anymore, obviously the scheduler must now select the new queue. That's the first one. Next one. When it switches from a running to a ready state. So that basically means after the time quanta has expired, sorry, you were actively running, but you are now interrupted. You've used up more than enough time now. Someone else is there. That's when we switch you away. Another one is when it switches from waiting to ready. So that's the only times you can't go from waiting directly into running. You have to go from waiting back into the ready queue again. And in certain cases, that is also a place where we allow the scheduler to run. So when the operating system detects something like that happening, it can say, okay, let's make some scheduling decisions right now. That's a possibility. And the last one is when the process itself terminates. So I've used up, my time quanta says 10 milliseconds, but you know what? I only used 4 milliseconds. Must it stay in the CPU to do nothing? No. When it's done, it's done. It's unloaded, finished. Someone else can now get the CPU. Right? So whenever it terminates, then the scheduler also comes into play. Now what they say here, this is important to realize. I like that. This is I like. Right. Scheduling under 1 and 4 is what we call non-preemptive. Non-preemptive basically means it's cooperative. Non-preemptive means the process itself says, I'm finished, I'm done, I voluntarily let go of the CPU. Right. All the other cases are preemptive. Preemptive means we interrupt. Preemptive is when I talk and then suddenly someone else interrupts me. That's preemptive. So if another lecturer comes in here and barges in and stops me from giving a lecture, that's preemptive. So in cases of 2 and 3, that's when it goes from a running to a ready state. That's preemptive, meaning we had to stop the running process. Or when we had to switch from waiting to ready, that's also preemptive. When we stop, again, the running process at that stage. They just mentioned here, when it's preemptive, consider access to shared data, what